We now know centrifugal pumps from the outside. In this section, we'll look at them from the inside and focus on internal components.
This is the third section of a four-section module on centrifugal pump principles. This section covers internal components.
External components are visible. Internal ones aren't until the pump is drained and disassembled.
Centrifugal pumps have six main internal components: the pump shaft, the impeller, wear rings, the volute, packing or mechanical seals, and bearings. The internal parts of a centrifugal pump are mounted on the pump shaft. It's a single piece of metal that's been machined to fit the pump perfectly. The shaft is usually made of stainless steel or some other corrosive-resistant material. And for a very practical reason, replacing broken or worn-out shafts is expensive. Some pumps have a shaft sleeve, or a metal cylinder that fits over the shaft and protects it from damage. It's easier and cheaper to replace this sleeve than the shaft itself. This circular device is an impeller. The impeller fits snugly on the shaft and is usually pressed on. It can be held in place by several methods, but the most common is with a key and key way. The impeller is the most critical part of a centrifugal pump. Why? Because its size and shape and the speed at which it turns determine pump capacity. There are three types of impellers: open, semi-open, and closed. Open impellers basically are vanes mounted on a shaft with just enough backing or shroud to keep the vanes rigid. Semi-open impellers are completely covered on one side of the vanes. Closed impellers have shrouds covering both sides of the vanes. They also have a central hole or eye on one or both sides. That hole lets fluid enter the impeller. Impellers are also classified as single or double suction. With single suction impellers, fluid can enter only one of the impeller's sides. That can cause problems such as imbalancing thrusts in the direction of the suction. In high volume or high discharge pressure pumps, that problem can be serious. It's resolved by using a double suction impeller. This type lets fluid enter both sides of the impeller. That makes the thrust generated on one side of the impeller counter the thrust from the other side. Pumps also come in stages, single or multiple. A single-stage pump will work fine for many applications and will raise pressure sufficiently. But there are times where more discharge pressure is needed. It's possible to raise that pressure by increasing the rotation speed of the impeller or by increasing the impeller size. But that's not generally done because of design and material limitations. That's where multi-stage pumps come in. They have two or more single-suction impellers mounted on a single shaft. The discharge port of the first impeller is directed to the suction port of the second, and so on through additional stages. When the fluid flows from one stage to the next, fluid pressure is increased. We know the impeller has to rotate. In centrifugal pumps, there's a space between the impeller and the casing so that the impeller won't rub against the casing. The space keeps both the impeller and the casing from wearing out, but also allows the fluid to leak back from the discharge to the suction side of the pump. Wear rings are installed in this space to control fluid leakage, but not to stop it altogether, since some leakage is important for lubrication and for counteracting the thrust and radial forces that build up inside the pump. When wear rings are attached to casing, they're called casing wear rings. These are called impeller wear rings. They're fitted to the impeller. Some centrifugal pumps are fitted with both casing and impeller wear rings. Remember the volute we talked about in Section 1? It's the chamber that's wider at the discharge nozzle than where the fluid leaves the impeller. That increased area lets the fluid slow down, and as it does, some of the fluid's kinetic energy is converted to pressure. Volute casings are either single or double. In the single type, the impeller and the volute are offset from each other to give room for the increasing size of the volute. But there can be a problem with this setup. Internal fluid action in the volute tends to set up unbalanced radial forces. To reduce those forces, some centrifugal pumps use a double volute casing. The double volute casing provides a second guiding vane to split and balance the internal radial forces. There are other advantages of double volute casings. They give the casing greater internal strength. They also reduce some of the stress load on the casing walls. There's an alternative to the volute. It's called a diffuser. It too has a chamber, but its chamber doesn't increase in size the same way a volute's does. Instead, there's a series of stationary vanes that are arranged around the impeller and direct the fluid outward from the impeller. The diffuser's vanes are further apart at their outermost point than at the edge of the impeller, so they create a series of widening chambers that function as a volute does in converting kinetic energy to pressure.
We've already seen a lot in this section. We'll examine packing and mechanical seals along with bearings before we take our next break. What's the purpose of packing? Simply to minimize leakage along the pump shaft.
It does that by sealing the clearance space between the shaft and the casing. A throat bushing keeps the gland follower from forcing the packing into the eye of the impeller. Packing is soft and pliable, usually made of cotton, asbestos, or flax. It's woven or braided into a continuous, square-shaped strand. Generally, it's coated with graphite or Teflon for lubrication, and since it's softer than the shaft, there's no damage to the shaft when it rubs against the packing. Still, additional lubrication is needed to cut friction to a minimum. Some fluid leaks out of the stuffing box. That's normal, and even good, because it provides more lubrication between the shaft and packing. Lantern rings are sometimes used to pressure lubricate the packing. These perforated metal rings are located between layers of packing in the stuffing box. They allow additional fluid from the gland sealing line to be injected into the stuffing box. That helps lubricate the packing. Look closely and you'll see that this piece called a gland follower fits into the open end of the stuffing box. It holds the packing and lantern ring in place against the throat bushing. If you adjust the gland follower's pressure against the other parts of the packing gland, you can regulate the flow and leakage rate of the fluid lubricant. Although many centrifugal pumps use braided packing in stuffing boxes, in the petroleum industry, mechanical seals are more and more the norm for three key reasons. They don't require leakage, which means greater safety when pumping hydrocarbons. They last far longer than packing, and they need less maintenance. Those points are especially important if the pump's in a hard-to-reach or inaccessible location. There's a wide range of mechanical seals available today, but they all have similar methods of operation and similar components. Rotating parts are attached to the shaft. Stationary parts are secured to the seal plate. The seal plate is bolted directly to the casing. The highly polished sealing faces of the rotating and stationary parts are held in contact by one or more springs. In this manner, a seal is made to prevent leakage. That's the typical structure for all mechanical seals. Let's go on to bearings. Bearings basically support the shaft and reduce friction as it rotates in the casing. They also do two other things, as you'll recall from Section 1. They control the forward and backward movement or thrust of the shaft, and they control the side-to-side or radial movement of the shaft. Centrifugal pumps use two kinds of bearings, ball bearings and sleeve bearings. Inside this circular ring are smooth metal balls that are free to roll as the shaft rotates. These are ball bearings. They're usually lubricated with oil or grease. The sleeve type is stationary. It's made of smooth metal cylinders in which the shaft rotates. Sleeve bearings are lubricated and cooled by a thin film of oil between the bearing surface and the shaft. That oil is brought to the sleeve by a ring oiler, or under pressure from a lube oil pump. The ring oiler transfers oil from an oil reservoir to the pump shaft and the sleeve bearings.
It's critical to lubricate bearings properly. Without adequate lubrication, bearings will overheat, rust, or corrode, and sooner or later cause the shaft to seize or stop. Centrifugal pumps can get hot, especially large pumps or those moving high-temperature fluids. Excess heat is most damaging to bearings and packing glands. Sometimes this heat is carried away by the ambient air or by fluid being pumped. When it's not, water jackets are frequently used to provide additional cooling.
These jackets are channels located in the casing, near bearing housings and packing glands. Water or another coolant is pumped through the channels to absorb the heat. That water or coolant is then either pumped to a sewer or to a heat exchanger to be cooled before it's recycled back through the water jackets.
We've covered a lot of information in this section. Let's stop now and review the manual. Review this section of the videotape, if you need to, before proceeding on to the last section on classifying centrifugal pumps.